Okay, so here we're going to be working out the numbers of protons, neutrons and electrons. So for this you're going to need a periodic table. If you look lithium up on the periodic table, then you'll see that lithium looks like this. The number at the bottom there is the number of protons, so nice and simply we can add it in over here. The number of neutrons is taken by taking the atomic mass and taking away the proton number. So 7 minus 3 gives us 4. And the electrons, because they're atoms, must equal the same as the proton number, so our electrons is 3. If we look up carbon, carbon is numbers like this. So again, exactly the same as we did it last time. 6 here is the proton number, the neutron number is atomic mass minus the proton number, which again is 6, and the electrons is equal to the proton number. Next one, lead, a little bit more tricky to find. Lead is Pb with the numbers 207 and 82. So at the bottom there is our proton number, so 82. I'm going to do 207 minus 82, which gives us the neutron number, which is 125. And similarly, the proton number is the same as the electron number, which is 82. And finally for iron, iron is Fe, which is 26, 56. So our proton number at the bottom here, 26. 56 minus 26 gives us 30 for the number of neutrons, and the electrons is 26. In these examples, you'll see that the isotopes are different to the periodic table numbers, so we're going to use the examples here rather than our periodic table to work it out, but it's exactly the same process as before. So again, the bottom number is the proton number, which is 5. The neutron number is the relative atomic mass minus the proton number, which again is 5, and the electron number will be the same. For uranium here, again, the proton number is 92, the number of neutrons is 235 minus 92, which gives us 143, and the electron number is the same as the proton number. Here we've got arsenic. So in this example, arsenic has got 33 protons, 79 minus 33 is 46 neutrons, and again the electron number being the same. This is another version of an isotope of arsenic. You can see the different numbers for the mass number represent the different numbers of neutrons. So it will still have the same number of protons because it's the same element, but this time it will have 71 minus 33, which would be 38, and the number of electrons again the same as the number of protons. For the challenge questions, so we've got tin 120 here. For this one we're going to need to use the periodic table to find tin. If you look up on your periodic table, then tin has a proton number of 50. So if we were going to write this, we could see that tin would look like this, so it would be Sn, which is 50. The mass number it's given us for this isotope here is 120. So therefore the number of neutrons will be 120 minus 50, which gives us 70, and electrons will be the same. Testing how well you remember your knowledge of your alpha particles. So we know that an alpha particle is a helium nuclei, helium obviously being 4, 2. So the number of protons at the bottom here is 2. The neutrons, 4 minus 2 is 2. The electrons is not 2 this time, it's 0. The reason it's 0 is because it's the helium nuclei, so it's just the nucleus and not the electrons which are found on the shells. Finally, for our beta particle, remember our definition for a beta particle, it's a fast-moving electron, so therefore it's going to have 1 electron and 0 of the others, because that's what it is. So if you're feeling confident at getting the number of subatomic particles in an atom of an element from the top, we can fill it in here. And if you're confident doing it from an isotope, not using the periodic table, but the information that's given to you, then cross it off here. Well done.